Let us talk about the qualitative analysis of substances. Qualitative analysis means the identification of the substances present in a compound. So, identification of constituents is known as qualitative analysis. Before going to the details of qualitative analysis, we have to familiarize some terms coming under this. So first one is common ion effect. Common ion effect. To make it clear, consider we have an electrolyte. So we have a weak electrolyte AB. So AB is a weak electrolyte, and consider this is A plus ions and this is B minus ions. So dissociation of the electrolyte AB gives A plus ions and B minus ions. So since this is a weak electrolyte, the dissociation of this electrolyte is not complete. That is, the dissociation as A plus B minus is not complete since this is a weak electrolyte. Suppose I add a strong electrolyte into this solution. I'm going to add a solution, a strong electrolyte, which is AC. That is A plus and C minus ions are in the strong electrolyte AC. So if we look at these two examples, A, B and AC, we can see that one of the ion in both electrolyte is common. That is, both the electrolyte contain A plus ions. Strong electrolyte as well as the weak electrolyte contain the ion A plus. We know strong electrolyte dissociate completely. So what happens when we add a strong electrolyte into a weak electrolyte? So we are going to add AC into AB. So the process occur here is the dissociation of the weak electrolyte suppressed by the addition of the strong electrolyte. And the phenomena is known as common ion effect. So, we can define common ion effect as the suppression of the dissociation of a weak electrolyte by the addition of a strong electrolyte containing a common ion. So, common ion effect is defined as the suppression of the dissociation of a weak electrolyte by the addition of a strong electrolyte containing a common ion. What may be the reason behind this? So let us take an example. I'm going to take a weak electrolyte, that is CH3COOH, acetic acid. Acetic acid is a weak electrolyte and its dissociation is as CH3COO minus ions plus H plus ions. Suppose I am going to add hydrochloric acid to acetic acid. hydrochloric acid HCl provide H plus ions and Cl minus ions. So when I'm adding hydrochloric acid to acetic acid, what happens is the concentration of H plus ions increases, because both the electrolyte contain this common ion H plus. So the concentration of the common ion or concentration of H plus ions will increase. So normally what happens is, here the concentration of H plus ions increases means the equilibrium shift towards left side. That is, the backward reaction occurs in a faster rate. So normally the dissociation of CH3COOH will be suppressed by the increasing concentration of the H plus ions. That is what happens when we add a strong electrolyte into a weak electrolyte. Equilibrium shift backwards and the dissociation of the weak electrolyte suppressed. Same way, the dissociation of ammonium hydroxide will be suppressed by the addition of ammonium chloride. Here ammonium chloride is a strong electrolyte and ammonium hydroxide is a weak electrolyte. So by the addition of ammonium chloride, the dissociation of ammonium hydroxide will suppress. The reason is both the electrolyte containing a common ion NH4 plus. Both the ions containing NH4 plus ions. That is common ion effect. The next term is solubility product. So consider a sparingly soluble salt. Let us take silver chloride, AgCl. So the dissociation of silver chloride is as Ag plus Cl minus. Imagine we are going to prepare the saturated solution of AgCl. So when we prepare saturated solution of AgCl, that is when we add water to AgCl crystals, at a particular state it forms a saturated solution. So in saturated solution, there is an equilibrium between the undissociated silver chloride and the dissociated ions. And the equilibrium constant K of this reaction is the concentration of the ions Ag plus Cl minus divided by concentration of AgCl. Since it is a saturated solution, we can take the concentration of solid substance as unity. AgCl is equal to 1. That is K equal to concentration of Ag plus into concentration of Cl minus divided by 1, and that is equal to Ag plus into Cl minus. And we can call this equilibrium constant as solubility product, equilibrium constant of solubility product, or KSP, that is solubility product. That is KSP, solubility product, equal to the concentration of the ions in the sparingly soluble salt AgCl, that is concentration of Ag plus into concentration of Cl minus. So solubility product is the product of the concentrations of the ions of an electrolyte at a given temperature. So this is a temperature dependent factor. That is why temperature is also mentioned in the definition. So solubility product is the product of the concentration of the ions in a saturated solution of an electrolyte at a given temperature. And one more thing we have to know when we studied about solubility product is that the conditions in which precipitation happens. So we have to compare the ionic concentration and the solubility product to find out whether the precipitation process occurs or not. If the ionic product exceeds the solubility product Ksp, then precipitation will occur. So precipitation occur when solubility product is lesser than the ionic product. Now let us talk about the significance of these two terms, that is significance of common ion effect and solubility product. Actually, in qualitative analysis, the qualitative mixtures are found out by mainly by precipitation methods. Or we can find out these inorganic compounds by detecting their color, their solubility, etc. Precipitation is also included in qualitative analysis. So in qualitative analysis, we are going to find out the cations and anions. So cations are normally precipitated as sulfides, hydroxides, or as carbonates. So here, how common ion effect and solubility product works in the detection of cations. Let us talk about the precipitation of sulfides. So here we are going to precipitate the metals as sulfides. So normally we use a weak acid, that is H2S, hydrogen sulfide, to precipitate the metals as their sulfides. Since H2S is a weak electrolyte, is dissociate as 2H plus plus S2 minus. The dissociation is very feeble. So when we add a strong electrolyte HCl, or when we add dilute hydrochloric acid to H2S, already the dissociation is weak. In addition to that, we added hydrochloric acid to it. So the dissociation even become weaker. So the sulfide ions, the concentration of sulfide ions are very less. For some metals, even the small concentration of sulfide ions is enough to precipitate. For example, copper, cadmium, bismuth, and arsenic, the sulfide ions present here is enough. That is, here ionic product exceed the solubility product. That is why these metals, that is copper, cadmium, bismuth, and arsenic precipitate in group 2. So copper, cadmium, bismuth, and arsenic precipitate in second group. Among these metals, the solubility product of cadmium is very high. So if we want to precipitate cadmium sulfide CdS, we need to dilute the hydrochloric acid added to this. That is, we have to add more water to the reaction mixture. Then only we'll get the precipitate of cadmium sulfide. So then, if we talk about the metals like manganese, cobalt, nickel, and zinc, their ionic product is lesser than the solubility product in this case. So these metals will not precipitate in second group. If you want to precipitate them, we need to pass hydrogen sulfide to ammoniacal solution. So if we need to precipitate manganese, cobalt, zinc and nickel, we need to prepare an ammoniacal solution of these metals. Ammoniacal solution of these metals. Then we have to pass H2S through this. Then only we will get the precipitate of these metals. Because the ammoniacal solution dissociate H2S completely. So complete dissociation of H2S occur in ammoniacal solution. So ionic product exceed solubility product and these metals precipitated in fourth group. So these metals are precipitated in fourth group. Some other metals are precipitated as their hydroxides. For example, iron, aluminium, chromium, etc. Fe3 plus, Al3 plus, Cr3 plus, etc. are precipitated as their hydroxide. Here, ammonium chloride is added to the weak electrolyte ammonium hydroxide. So, ammonium hydroxide dissociated as NH4 plus and OH minus ions. So when we add ammonium chloride into ammonium hydroxide, the concentration of the ions become lesser by common ion effect. But if this mixture, that is ammonium chloride, ammonium hydroxide solution is added into an inorganic mixture containing any of these metals, precipitate will be formed there. That is, hydroxide precipitate will form. Because for these elements, for these metals, ionic product is enough to precipitate. So here for these metals, ionic product exceed solubility product. Even the lower ionic product is enough to precipitate iron hydroxide, aluminium hydroxide or chromium hydroxide. So these metals precipitate in group 3. But metals like magnesium, zinc will not precipitate in ammonium hydroxide, ammonium chloride solution because their solubility product is much higher than ionic product. And some metals precipitate as carbonates. For example, if we add ammonium carbonate to some inorganic compounds, solubility product of the metals like barium, calcium and the strontium, their ionic product exceed the solubility product. So these metals precipitate as barium carbonate or calcium carbonate. strontium carbonate, etc. And these metals precipitate in group 5.